Delphi model. We ran each CFD, which we ran in CFD, we played with it and optimized it, and got a set of resistors here. What you see here is a set of resistors. Again, there are resistors, passive, some of them passive, some of them active. You can have a CPU is an active component. And then we have fluid nodes and rings, which represent the pressure drop and mass flow rate. So actually what we have is you give me the boundary conditions on the module, and all the boundary conditions, and I'll give you the temperature of each component in real time. It's very easy to solve it. It's just a network of components. I'll give you the pressure drop also, and you'll get it in real time. So what it means is that we reduced 220,000 cells of a CFD to a generic network of 100 nodes and connectors. So who asked the question about what's the point of using it?
I asked about the limitations and the disadvantages.
Okay, so the disadvantages is that you cannot work outside of the range of validity. The advantage is that you can always have another verification point added. You can always have another verification point added to the generic network. I mean, you can always make the model more, you need to check that you don't have, because you're talking about fans and flows, and you need to check that some important things that we will not go into, that you don't have something like bifurcations inside simulation. What is a bifurcation? It's a total change of phenomenology, okay? Like the flow laminarizes somewhere, or it turns turbulent, okay? This could pose as a problem to a reduced order model, because you can't really do this kind of, average between points. Except that you get a real-time or small cell count. You can get what you want actually from a module. What you want really from a module is what's the temperature of each component, what's pressure drop, and what's the point of operation of the fan. Nothing else really interests you most of the time. Okay?
Okay,
so 120,000 cells reduced to 100 generic networks. Runtime of maybe not a lot, but if this is this little module here, you see the error, very small, very small. But if this is only one module from 12 modules inside a cabinet, matched by the boundary condition, each of them has its own boundary conditions, but it doesn't matter because each of them has its own ROM. Then you can get on real-time results for something which would be kind of, I would call it, as a thermal engineer, stupid thing to do, to analyze a cabinet with small modules to the level of, the aspect ratio between the smallest component and the cabinet is so high that that would be stupid to do, even as a CFD. Did I answer your question, Avishai?
Yes and no. not fully answered because maybe I'm just a beginner, but I think the reduced order model is not fully understood by me, and therefore I can't make the comparison well.
What is not fully understood? I mean, you can turn conduction route with the analogy of potential equals resistance times current to delta T equals heat transfer Q times thermal resistor. So there's a one-to-one thing you can use, exactly like you use when you have, you can use the same thing with laws of, I don't know, there are many, okay? But the point is this thing is 3D, and is to turn a 3D model which has a much larger set of order of magnitude, like 220,000 cells, and turn it into something which is arithmetic. Yes, its range of validity is very limited. A CFD, when you have boundary conditions and you know what you are doing, you can solve always and get the right answer. Here, it's not the same. But for the range of validity that you have decided upon, you can get the good enough answer for what you are interested for. I mean, you are not interested in the temperature here. You are not interested what's the vorticity here. You can get that from CFD. You can get every point, you can get the lambda 2 CFD. But you are not interested in that. You are only interested in what's the temperature of this memory here. What is the point of operation of the fan, and what is the temperature of this or the other, or what is the temperature of the CPU. Other than that, you don't care about anything.
I understand.
Okay, so
yes.
you can turn these to these. Of course, you lose a lot of data. You lose. What do you mean a lot? You lose everything, but the temperature in these nodes. Okay, the temperature of or the mass flow rate in these nodes.
Okay, thanks. Understand.
Yeah. Yeah. You have many ways to do that, actually. You have many laws that say if you had a pipe, then you have system pressure drops. Usually goes like the pressure goes like the mass flow, the volume flow rate squared. So if you have a set of boundary conditions, you run the CFD, you get the numbers, and you get the system pressure drop, which is a PQ curve, which looks like a parabola for the boundary conditions that you have. And then there's no problem. I mean, you can do that for a few sections, another section, another section, another section. Yeah, it takes a lot of work to do the ROM itself. But then after that, you don't need the ROM takes time. It's a big set of, let's say, 64 CFD you have to solve. But then afterwards, you can use that as a real-time tool for solving problems in real time in the range of validity. But there's no problem to find a pressure drop inside the area. You just run the CFD and check the pressure drop. You'll probably get a system pressure drop of kind of parabola, a steep parabola if it's in a if there are many disturbances to the flow, flat parabola if it's kind of an open system, but that's it. SimCenter even in Star CCM has a ROM configuration, which means that they'll tell you choose for yourself 3 point of operations for the fan, or choose 16 of them, choose 16 temperatures, choose 16 I don't know, ambient conditions outside of the box to do some kind of, and then it'll start running the reduce order model. I wish I could have showed you. I know I had it. This is me off with that. I can see it now. ROM builder. Here you are. Open up. Please open up. Here you see a ROM builder. Okay. You see, I have many. What? Okay. So this is a ROM I did for if you know what an FFR is. An FFR is a device which goes inside the body of a person, and it finds constrictions. It takes the diastole and it takes the blood pressure difference, and then decides if it has a value. The value doesn't matter because doctors don't care about engineers about values. But if it's above 0.7, then there is we need to operate. We need to do some kind of ablation or something like that. So what we did here is we took 5 archetypes of blood vessels. There seems to be not many types of archetypes of blood vessels in the human body. There are about 6 or 7 which are interested. And what we did is we built a ROM, which depends on we just ran it for a few Reynolds numbers, and we extracted the FFR for each of them. We extracted the blood pressure we had many cases for the blood pressure difference. And we had a model which was a model of a reduced order model. The geometry was acquired by X-ray, and then by machine learning transferred to a model. And then, according to the geometry also, which was also part of the ROM, we devised them reduce order model, which can predict the FFR in the area of constriction. So this had many points, I think 64 points. You can see the FFR location, the FFR this, the inlet. There are many things that go inside, but once you have the ROM, then you have a very simple tool which you can do, which would actually in this case replace invasive procedure with an X-ray, machine learning, and a little bit of CFD. So that's how ROM is important. Very. Are we done with ROMs, or any questions about ROMs? Yeah. I just told you. Fluent, you just saw it. You just saw it here. I mean, you just saw it. This is Fluent's reduced order model configuration. I mean, it's so easy to use it that you really feel like a retard when then you have a ROM post processor. You have like a lever you pull for the pressure, for the velocity, the Reynolds number. And
hello,
the customer doesn't even need to have the processor of post processor of Fluent. He can download the free ROM viewer. There's a general file that goes out, and he can use that and see the results. So both StarCCM and Fluent have now ROM configurations like this.
Yeah, we cannot see your screen actually other than that PPT. So
you cannot see what?
We cannot see the screen which you are sharing, like the explanation screen which we are talking about right now. We were not able to see it. We are only able to see that material, PPT material which you gave us initially. So your screen is not able to share that material.
You cannot see the screen?
Now we can
only see only the PowerPoint.
Only the PowerPoint we are able to see. We are not able to see the other screen which you want us to show.
Okay. Let me share. I see. Stupid. Always do that. Now you can see, right?
Yes.
Okay, you see how simple this is? You take a bunch of input parameters, a bunch of output parameter which interests you, range of validity for many parameters, and then you simply solve the CFD after CFD on batch, which takes a lot of time, but time on a cluster of I don't know, 96 processors for such flow, we used blood as a Newtonian fluid. We use the turbulence model because you have constrictions and you might have turbulence there. The transition model, but it will be too much. And then after it solves all this, you get the ROM. I mean, you get the reduced order model. You get a screen, a new screen. The screen is a post processor. Then you have like levers, and you play with the input parameters and see how the results change. Very simple. And the client can download from, I think, 100 kinds of viewers. There is a general file for reduced order models. Because it's simply not big data, medium data thing. It's just numbers and interpolations. And he can use it for free without the Fluent viewer. Same on StarCCM. Okay? Are we okay? Any more questions about the reduced order model?
Yeah. Tom?
Yeah.
So we're basically building a response surface here. and we are monitoring the response of a particular output variable to the change in the input variable without,
Yes.
without solving
But we have a
explicitly.
range of validity. We have for each let's say Reynolds number, we have many geometries of constriction that we check.
Mm-hmm. Okay.
Okay, it's a set. It's like a matrix with n over n,
Mm-hmm.
but it's still a lot less than solving CFD.
Yeah.
How are we? Are we done with the ROM? If anyone wants a reference about the ROM, you can contact me on LinkedIn. I guess most of you know me from LinkedIn, and I'll give you something good. Okay, which would explain you exactly how to use reduced order model, what it does. So let's continue. Share the screen. Go to the board level. The board level, the PCB. What we usually do, we have two things that we do. The old version and the one that I believe in, and I'll tell you in a second why I believe in it, is to look at the PCB. The PCB has FR4 layers of kind of plastic, kind of perspex, which is non-conductive, not very conductive. And it has ground layers, signal layers, power layers, okay? Each of them has difference. I mean, a ground layer could be filled with copper, almost 90%. A signal layer could be a lot less, okay? So we can assume how much there is, how much copper there is in each and every layer. What's the height? And we have these equations here to tell us what is the normal to the PCB conduction and what is the in plane. In plane is usually an order of magnitude higher than the normal conductance because it's hard for the heat to go through the FR4. Okay? So a tip, verify this. Yeah, that's something that people, that's a little joke here. I mean, people usually think Z is up. Sometimes it's not. And they get, so take a good look on your, set of origin. Apply the effect of vias on the normal conductivity. Okay, most components have vias, thermal vias. The thermal vias you can get from the designer, the board designer, or the one who actually does the board. But what it does, it improves the normal to plane, the in-plane conductance stays the same, but it's like a pipe of copper, which improves, filled with copper sometimes even, and it improves the normal to plane conductance by a lot, sometimes by a lot, if it's closed, if it's done right. So it's very easy to make an Excel sheet and
compute it, but you need to you know, if you, because it could be an order of magnitude difference between no vias and vias. Okay, so you need to get it more on iSpec. Okay, the other thing that you can do, now this is on iSpec, but you can also do it on FlowTerm. I think FlowTerm is a lot better for this even. Is you can read an IDX file. It's a file from the designer, the board designer himself, okay, with all the traces and everything. And it can give you the ODD++ file or any kind of the board design file. And it could give you a few things. It could give you a full picture if you want. It can give you areas where more copper and areas where you have less copper, which means you get look at it as if it was 3D. And then you have this square here, which has higher normal to plane conductance. I think that in most cases, this kind of method is anal, because most of what we do is use two resistor models, which means that if I have for this chip here a two resistor model, then it's isothermic upstairs on the top of the chip and on the bottom of the chip. And there's really no meaning to the local temperature around the chip. So results when you solve for PCBs are generally not local. They're more general. That's why nice pack. Okay, the system level. The system level is very important. And you can see kind of if it works. Does it work? I don't know. Okay, choosing a fan. All of you know fan laws. Okay. I mean, now that it's going closing out the time, it's going to happen again. Okay, so everybody knows, everybody knows fan laws, okay? Fan laws allows us to actually let's say equate fans, but what I think is that if you don't know beforehand which fan you need to use for your application, then go and ask someone who does, because it's a problem. There's no way that I see an electronic chassis and don't know which fan I need to use. It can't happen. What you see here, there are different kinds of fans. This fan is a vane axle fan. It's a fan that is more for high pressure and average CFM, average volume flow rate. Your computer at home has a tube axial fan, which works against low pressure and supplies a lot of air. There are many demands for fan besides the point of operation. I mean, this fan here is called Rotron Aximax 2. So first of all, you need to work on there's a working zone for the fan. You work only on this zone here, which starts here and ends here if it's free flow. But you wouldn't use this fan for free if you probably had a point of operation which needs a lot of inches of water. This area is not stable, so you won't work here. If you have a simulation or if you do an experiment, you'll actually see it ticking from one to another. It destroys the fan, and this fan screams. So there's a lot you need to know about fans before you decide which fan you use. It's not only the amount of flow that you need, it's the whether you need to work on height, because the curve, this curve you see here, is going down as the density divided by the density at sea level. So I mean, if you are at, if this is for an F-16, then you have about 1/12 of the density, which means every cube has a lot more molecules of air, a lot less molecules of air, and the fan curve will go down here and will be something flat like this. So you need to think about altitude effects. Altitude effects goes according to the actual density divided by sea level density. Sea level density is the average conditions you get here. Okay? So you need to take this into account. Watch for density variation effects. But if you don't know which fan belongs to your configuration, then you need to consult someone. Don't try on your own. There are many other issues with fans. Again, I'm saying there's the issue of power. How much power do you take from the system? You can really cause problems. There's a measure of how much power the fan can. If you want to use it as a push fan, then you push all the power of the fan as heat to the electronic device. On the other hand, if you use it as an exhaust fan, it's better for environmental conditions, and you don't push the heat of the power of the fan itself inside, but you get a low pressure inside, right? Because you need to get the pressure back to ambient pressure. Then if you have holes, if you have, I don't know, made some change the chassis to lose a little bit of weight, and you don't have the right hose to take water out, you may have problems with suction of water to the system. So if you don't know which fan to use, if you don't have enough experience, always consult someone. There's also the issue of noise. This fan is noisy as hell. I mean, it actually screams when it works. And it could be a problem, a real problem. It could be even a restriction. CFD analysis. Let's take a look at a fan choice for actual analysis. Any questions? Hello?
No, thanks.
No, thanks. Okay. Now you see here is the internal volume of a chassis. All of this is water, not water, sorry, air. Okay? This is not a solid. The solid is around it. Okay? This is a solid surface, of course. It's the boundary for the fluid. We extracted it from the model, okay? So we have a push fan here, and we have an exhaust fan, and we want to check what the effect. We want to optimize these fans. These fans are working in series. Fans which are working in series means that when they are totally closed, then you get double the pressure drop. I will see it in a second. What is important that I wanted to show in this lecture is that CFD does count. It's not like you put your boundary conditions, you do your CFD, you get your results, and everything's okay, grand. It's not like that. It's not like that at all, and here you're going to see why. The air comes in, this is a push fan, the air comes from here. It can go anywhere. It will go wherever it's most easy for it to go. Okay, right? Was the least resistance. Okay, and it's very important that I catch the right way that the air flows through here. Otherwise, I can get totally erroneous results. So the mesh was generated here. It was generated with ANSYS Fluent. The surface mesh expected proximity 6 cells curvature. It means that the resolution was such that the turbulent boundary layer was in full resolution, which means we fully modeled the turbulent boundary layer, which is comprised of a viscous sublayer, log layer, and a defect layer, and the free stream. I'm writing it, it looks like Chinese for most of you, but it's important. And we had more than 10 layers with an aspect ratio which is big, because the first cell away from the wall is really, really small, but it's long. So the aspect ratio is big, but it's no problem.